Okay, hello everyone. Welcome to my channel. So, have you ever walked into your office or a meeting room at 8 a.m. and it's freezing cold? Every light is turned on to maximum brightness, but there's no one there. That's what we call the invisible money pit. So, facility manager estimate that commercial building wastes a huge amount of money and energy simply because of system like air conditioning, lighting. They're really running on a rigid schedule rather than reacting to the actual human behavior. So today in this video, I will try to fix that. We are taking a data set from a smart IoT setup, and we are going to use Python to analyze it. And by the end of this video, we will not just have the chart or the plot, we'll have a concrete plan to save the energy, to optimize it, and maybe even save some money for the company. So we're going to look at occupancy pattern, temperature correlation, and finally the recommendation. Okay, so let's dive into the data. Okay, so first let's talk about the raw material. So we have a data set here called Smart IoT, a Smart Office IoT.csv. Sorry. So this represents the sensor reading from this room labeled Room A, covering 3 days in early March. Uh, Usually IoT sensors dump data every seconds or minutes, but for this analysis, we aggregate it to make it hourly, to basically make it easier to digest. So here's three specific variables that we're tracking. First, of course, I mean four specific variable. Oh my god. First one is the timestamp, of course. Second one is the occupancy. This is simply a head count of how many people are in the room. Next is the temperature. So the ambient room temperature is, of course, in Celsius. And lastly, light, measured in lumens. Okay, so when we load this into our Python environment using Panda library, you see a standard time series format. For example, if you look at March 1st at 11 a.m., we see that there are 10 people in the room. Let's see. Here. And the temperature is 26.2 degree and light was at 600 lumens. So on its own, this is just numbers. It tells us what happened, but it doesn't really tell us why or what we should do about it. And this is where our analysis comes in. So we're going to break this down into three steps: occupancy planning, correlation check, and optimization logic. Okay, first is the planning itself. So we need to understand the human rhythm when the room is actually being used. So we run a script to group our data by the hours of the day to find the average occupancy. Think of it as finding the heartbeat of the office. And here's what the data showed us. The office is very distinct, have a very distinct personality. We identified specific busy hours or peak time. These are at 10 a.m., 11 a.m., and 4 p.m. Okay, this makes sense, right? 10 and 11 a.m. are prime time for mid-morning meetings before lunch. Then everyone leaves for lunch, and then we see a spike again 4 p.m. for this end of day wrap-up session. But equally important, we identified the quiet hours. So this are 8 a.m.s, 2 p.m.s, and 5 p.m.s. So why does this matter? Well, if I'm a facility manager and I sit at 8 a.m., we typically have a very low occupancy, maybe just one or two people, but my building system are running at 100% capacity. That is a red flag. The data is telling us that morning rush doesn't actually start until 10 a.m. So why are we treating 8 a.m. like it's peak hours? Now, let's go a little more scientific. So does the number of people in the room actually impact the temperature? Well, obviously yes, but in a perfectly optimized building, the answer should be no. A perfect HVAC system will detect people entering the room and just cool down the room itself to counteract their body heat. So we calculate this using a Pearson correlation. This is a statistic that measures the linear relationship between two things. So, and our analysis returned a result of zero point 0.6. That classified as medium or high positive correlation. So this is the TLDR. So occupancy goes up, the temperature also goes up. This tells us that there's something crucial about our HVAC system. It is reactive, not proactive. The system is struggling to keep up. It lets the room get hot when people enter rather than maintaining a steady climate. If this number were close to zero, it would mean that our AC is perfect since it's zero point 0.6. But we know that our AC is lagging behind the crowd. Okay, this is the heat map. As you can see, zero point 0.6, temperature, and occupancy. This is the scatter plot. As you can see, it goes up linearly. Okay, this is the solution. Okay, so here we have a pattern and we have the physics now. Now let's turn this code. Uh, now let's turn this into some simple code that makes decision. So this is the optimization script. This is basic if else code. Okay. We found that there are three big recommendations for the data. So number one is the 8 a.m. AC adjustment. Our script looked for times when occupancy was low, but the temperature was high. It flags, of course, 8 a.m. immediately. The data shows that we are cooling the room down to 23 or 24 degrees, but there's nobody there. The fix? We let the room stays warmer a bit, maybe like 25 or 26 degree until more people arrive, usually 30 minutes before 10 a.m. Number two is the post-launch lighting fix. So the code looked for hours when the room was quiet, but light were blazing. It flags 8 a.m., 2 p.m., and 5 p.m. Again, 8 a.m. Okay, look at the data for 2 p.m. Occupancy drops to about 3 or 4 people. There are likely people that are still at lunch or working at their desk. Yet the lights are over 500 lumens. That is a huge waste of electricity. And the fix is to automate the dimmers. If occupancy drops below 5, we can dim the light by 30%. This is a smart obvious after all. And lastly, uh, because we identified that the busy period starts at 10 a.m., we can stop guessing. The fix, instead of turning the AC on 8 a.m., oh, we schedule a pre-cooling, like what I said earlier, 30 minutes before the peak, so at 9:30 a.m. This ensures comfort for meeting rush without wasting any energy for hours prior. Okay, so what did we accomplish here? We took a simple CSV files with 3 days of data and using just a few lines of Python, we diagnose a lagging HVAC system. We identify the exact hours where energy is being wasted and create a new operating schedule that matches the actual human behavior of room A. This is this is why IoT data analysis is important. It stops us from running our building based on guess and starts running them based on facts. Well, I think that's all you'll get from me. My name is Zhafif Naryama with the student number of 2361 and 0263 from Bachelor of Informatics 23. Okay,